All right, so now we are going to talk about word embeddings. So first of all, what is motivation for word embeddings? Here is a sample of Donald Trump's Twitter. So we have the text of each tweet. We have the timestamp. We have retweet count. There are some more variables that I'm not showing here, but we are going to work with text. So at the moment, I'm not going to be interested in other variables. So just text. The total number of tweets is almost 20,000. And well, just as a little bit of data exploration, here is the distribution of the number of characters in a tweet. Now, I'm going to clean the text by changing everything to lowercase and deleting punctuation and, well, other characters. So except for alphabet and numbers. Right? And now, whatever words appear in this clean text, they are basically going to become my features. So all individual words that appear here, they are going to become predictors of features in the data. Well, maybe predictors is a wrong word because I'm not going to predict anything. So features is the right word. The text can be visualized as a word cloud. So here is the word cloud. So you can stare at it, see what kind of, to get some idea of what happens in Donald Trump's Twitter. The most common word here is the real Donald Trump. So this is, I guess it's probably just appears maybe like in every tweet. I'm not sure. But... Okay, here is the histogram of a logarithm of a retweet count. So if you plot the histogram of the raw retweet count, it's going to be very, very skewed. But if you take the log of retweet count, you will see some nice distribution. It is a bimodal distribution. And apparently these are tweets that did not go viral, and these are tweets that went viral. So these are probably viral tweets. Right? So the retweet count, the logarithm is around 10. So the retweet count is about e to the 10, so which is quite low. Okay. So document term matrix is the matrix whose rows represent documents. In this case, documents are tweets, individual tweets. So when we process a large text, then documents could be individual sentences or paragraphs. So columns of the document term matrix represent words in our vocabulary. So here is a small sample of document term matrix, or DTM, for Trump's Twitter. Right? So this number means the following thing. So it means that in the first tweet, the word for appears 2 times. So if you read the first tweet, then you will see that the word for appears 2 times. And the word see does not appear in the first tweet. So these are dimensions of DTM. So the number of documents is around 20,000, and the number of terms or words is around 28,000. So it is even bigger than the number of documents, and it is typically a case with natural language processing. Now, this is really too large, right? But even if we decide to say remove some of the terms, so let's say we're going to remove words that appear fewer than 10 times in fewer than, well, that appear in fewer than 10 tweets. So the number of the number of variables or features, not predictors. I'm not going to predict anything. So the number of features is still going to be very large. Right? So in order to reduce the number of features to a reasonable number, to like 50 or 100 or maybe a few hundred, I really need to set this threshold very high. And by doing this, I'm going to kill a lot of meaningful words that appear in my documents. So which is why using a document term matrix, well, reducing it may not be a good idea, but using the full document term matrix may be just too costly. And this is the motivation of to introduce some clever algorithms to reduce the size of the document term matrix. Right. So in word embeddings, we are going to kind of to come up with a function that assigns vectors to words. So it's going to be a function from the set of words to the d-dimensional space, where d is going to be relatively small, so typically 100 or 200. Okay, so that was all for the first chunk of the lecture, so please do the quiz.